Welcome to this video series on improving the performance of your runs on HPC clusters. Today we're going to talk about what performance actually means in the context of high performance computing and why it's important to be clear about your goals before you start optimizing. My name is Chris Fry and I'm with Trends of Synergy, creator of the HPC Performance Tools Survey, which is a lightweight tool for measuring the performance of HPC applications. This is the first of a series of videos on HPC performance analysis based on the work of Dr. Douglas Pace of Sandia Laboratories. Let me start with a simple question. Which is faster, a sports car or a bus? Your immediate answer is probably the sports car, obviously. But what if you need to get a football team across town? Suddenly the bus looks pretty good. Or if you're traveling from Los Angeles to New York, maybe a plane makes more sense than either one. The point is that faster depends entirely on what you're trying to accomplish. The same is true for HPC. When running jobs on an HPC cluster, you're typically optimizing for one of two things: turnaround time or efficiency. Faster turnaround time means getting your results sooner. This helps you meet deadlines, stay focused, and move on to the next task. But speeding up a job often means throwing more resources at it, which can actually make your job less efficient. Greater efficiency means using fewer resources to get the same work done. This lets you run more jobs with your allocation and makes you a good neighbor on a shared system. But running more efficiently sometimes means your job takes longer on the wall clock. These two goals are often in tension. Adding more nodes might cut your wall time in half, but you might use more than twice the node hours. Running on fewer nodes saves resources, but your results come back later. Let's look at 3 scenarios you might find yourself in. First, you need a single job done as fast as possible. Maybe you have a paper deadline or your team is waiting on results. In this case, you will run on as many nodes as will give you a meaningful speed up. You'll need to look at memory requirements, MPI overhead, and I/O time to find your scaling limit. Second, you're not time constrained and want to make the most of your allocation. Here you should run on the fewest nodes that have enough memory to fit your job. This maximizes efficiency and leaves resources available for when you really need them. Third, you have an ensemble of jobs to run. Now you're competing with yourself for resources. The strategy is to run each job on the minimum nodes needed for memory and then pack as many jobs as you can into your available allocation. If you still have nodes left over, increase the number of nodes for each job. However, you can do that until your allocation is filled. Before we go further, let's define some terms we'll use throughout this series. Job turnaround time is the total time from when you submit a job to when it completes. This includes both the time spent waiting in the queue and the time spent actually running. Job queuing time, also called wait time, is how long your job sits in the queue before it starts. Job execution time, also called wall time or run time, is how long your job actually runs once it starts. Job efficiency compares how much work gets done relative to a standard. An efficiency of 1.0 means you're matching the baseline. Less than 1.0 means you're doing worse. Greater than 1.0 means you're doing better. Compute time in this series usually means node hours, the number of nodes you've allocated multiplied by the hours you use them. So how do we actually make informed decisions about our jobs? We need data. Here's what we can measure on an HPC cluster. Physical memory, how much is available, how much is free, and how much is in use at the level of individual ranks, nodes, or the entire job. Dynamic memory usage, including stack and heap allocations as they change over time. Time breakdowns, wall time, user time, system time, MPI time, and I/O time. These tell you where your job is actually spending its cycles. The distribution of ranks across nodes, are they spread evenly or bunched up? Kernel affinity for each rank and thread, which CPUs are they allowed to run on? And application-specific metrics like grind time, cycle time, or AMR redistribution time, if your code reports them. With this data, you can predict what will happen when you scale your job up or down. If you increase the number of nodes, you might reduce wall clock time, but you may also increase the overhead of parallel operations like MPI communication. Is the trade-off worth it? The data tells you. If you decrease the number of nodes, you may reduce that parallel overhead and make your job more efficient. But now each node has to hold more data in its memory. Will it fit? Again, the data tells you. Affinity settings help you distribute your work effectively. When ranks are spread evenly across processors and NUMA domains, you get better memory performance and balanced compute loads. When ranks are allowed to migrate across boundaries or when they're bunched up on a few cores, performance suffers. And by looking at the balance between user time, system time, and I/O time, you can tune how often you write checkpoint and visualization files. Maybe you're spending too much time on I/O and not enough time on actual computation. Or maybe you can save more frames and get a better picture of what's happening in your simulation. Here's the good news. You have real control over these factors. You control the number of nodes. More nodes means more memory and faster execution, but perhaps lower efficiency. Fewer nodes means higher efficiency, but longer runtimes. You control how much work is distributed. Good load balancing means better use of power, cooling, network bandwidth, memory bandwidth, and compute resources. A well-balanced job runs faster while using fewer resources. And you often control job parameters like mesh refinement, checkpoint frequency, and visualization output. These are knobs you can turn once you understand where your time is going. So before you start tuning your job, ask yourself, what am I actually trying to achieve? Am I racing a deadline or am I trying to stretch my allocation? The answer will guide every decision that follows. In the next video, we'll introduce Trends Survey, the HPC performance tool, and show how it helps you answer key questions about your job's resource usage. If you like this video, please give it a thumbs up and subscribe to our channel. You can also turn on notifications so that you'll get notified when we have a new video up. Thanks so much for your time, and we'll talk to you later.